So now that we looked at Kinetics 1 and we saw the phase diagrams, we know that the more stable is exothermic, less stable is endothermic. We're going to start looking at table I in our reference table and what makes something spontaneous versus non-spontaneous. All right, first off, table I gives you the heat of reaction at 101.3 kPa and 298 Kelvin or 25 degrees Celsius. So it says at the bottom, minus signs indicate exothermic. So any of these that are negative are exothermic. Remember, exothermic means they end lower, meaning that they are more stable. The first 6 right here are combustion. How do you know? Because it equals whatever this is, gives you some type of carbon plus oxygen, gives you carbon dioxide and water. That's how you know those are combustion, carbon dioxide and water. The center section, right about here, that's all, well, it lists a bunch of synthesis. You see 1 + 1 = 2. You see a lot of that all in the middle right here. While the synthesis reactions tend to be exothermic, negative, you got a bunch of those negatives because it's building bonds. So it's going to be exothermic. It's going to give off energy. They may be endothermic. So we got lots of exo, got a couple endo. There's 2 right there, a couple right here. The heat of formation is defined as energy change associated with the production of 1 mole of a compound from its element. So most of these are 1 mole at STP. Okay, so the reaction of carbon and oxygen goes to carbon dioxide. It shows the formation of the 1 mole to be negative 393.5 kilojoules per mole per 1 mole. But the net reaction of N2 plus O2 gas goes to 2N2O, says it forms 2 moles at, hold on, I'm having an issue. Shows the formation of 2 moles of NO2. The delta H is plus 91.3 per 1 mole. So it'd be half of what is there. So anything with the 2 in front of it, you'd have to half it to find out what 1 mole would be. All right, so most of these on the bottom right here, those are dissolving. How do you know? Because you're adding whatever it is to water. KNO3, NOH, ammonium chloride, ammonium nitrate, sodium chloride, lithium bromide, potassium nitrate, all of that is added to water, making an aqueous solution. And you can see aqueous. All right. And at the very, very bottom, H plus OH gives you H2O. It's extremely stable. Its production is going to be exothermic. Okay? So, oops, sorry. For the reaction, 2 carbons and 2 hydrogens. Okay, for the following reaction, I'm okay over here. 2 carbons plus 2 hydrogen gas, that's solid gas, gives you C2H4 gas. Is it more or less stable? Remember what we were talking about with the phase diagrams and being stable and being not stable. You want the one that has the line ending down, aka exothermic. So anything that is negative is going to be more stable. Is the product more or less stable than the reactants? The reactants are here. Here's the products. So let's see. What is CnH2? CnH2. Right here. And it is positive meaning it's endothermic, which means that we're starting down here and ending up here in our phase diagram. It's less stable. Heat of reaction is positive, indicating exothermic. Products are higher energy and less stable. Which of the following releases the most energy when combined with oxygen? I can move myself over here again. So N2 plus O2, N2 plus O2, those are positive, meaning endothermic. Not, definitely not. CH4 all the way up here, we got negative 890 because that's with oxygen. Let's look at glucose or sugar. It makes negative 2,804. That's going to be your winner. N2 doesn't release energy, it absorbs it. Both reactions involving N2 are endothermic or positive. So those don't work, but both CH4 and sugar release energy, but glucose has a larger magnitude. So, okay, let's look at this. What is the delta H when 90 grams of glucose is burned with a molecular weight of 90 grams per mole? Again, you got to remember, if I have grams here and I'm given the gram formula weight and I got to figure out how many moles, 90 divided by 180, that's half. So I half a mole, so I need half of this glucose right here. Half is negative. Keep the negative. Don't ever get rid of it. 1402 kilojoules per mole. Again, right here, the reaction listed indicates the combustion of 1 mole of glucose released is 2,804 kilojoules. It's negative, by the way, it's released. So 90 grams is half a mole, which will release half the energy. Negative sign is needed on the answer. Okay, spontaneous processes. Okay, so spontaneous reactions occur without outside intervention. Examples, iron rusting. Iron will rust when presented with oxygen. Heat flowing from hot to cold. You put your hand on a cold surface, the heat is going to go from your body to that cold surface to melt or try to melt that surface. Ice melting, you put ice inside of a liquid beverage to cool your beverage down because the ice melts going from your warm glass into the ice, melting it down. Why do reactions proceed readily in one direction and not the other? Well, spontaneity. Common characteristics of Spontaneitis systems are decrease in delta H. So exothermic processes are normally spontaneous. Endothermic processes are normally not spontaneous. So negative, spontaneous, positive, not spontaneous. So what are some more things? Increase in entropy, delta S, entropy, chaos, like this bedroom right here. So increase in entropy, systems become more random. The more disordered or random a system, the larger the entropy. Natural law indicates reaction go in the direction that leads to more disorder, more chaos. So there are far more combinations of disordered states for a given system, meaning that the probability of a disordered state happening is more than an ordered state. So probability is favoring disordered. So what affects entropy? Let's look at some phases. So solids to liquids to gases. If you're looking at this, we want more disorder. This right here, there's not a lot of disorder. It is stuck together. Solids are stuck. All they do is vibrate. And then you go to a liquid. So they vibrate and they move around, they rotate a little bit. And then you have gas where they vibrate, rotate, and translate. They bounce off the walls. They get as far apart as possible. That is chaos. Random. Gases. Entropy, gases. How about at identical temperatures, solids and aqueous solutions? So solids, again, right like this, they don't move much. But if I dissolve it, I'm going from this to kind of like a looser, disordered state. Entropy. Number of moles. If a reaction produces more moles of a product, unless it involves less moles of gas, it shows an increase in entropy, more disorder. So you see more order here. 1, 2, 3, 4, 5. And they're kind of just there. If I break them up, I'm going to have, number one, more of them and all over the place, more disorder. Synthesis reactions generally show a decrease in entropy. Well, why is that? I'm going from two separate things and I'm shoving them together to be more ordered, less entropy. Temperature for identical molecules. So a molecule at greater temperatures show greater motion, greater disorder. So you have more chaos with hotter than colder stuff. Volume. If I decrease the volume, I give more space, more room to stretch out and be disordered. Whereas if I squish it, it is getting more ordered because you have less room to go. So here's a little exercise. Indicate whether each of the following reaction produces an increase or decrease in entropy. Solids to gas, I'm going from here to here. I'm increasing my entropy. I'm going from a solid in gas to a solid. I'm adding two things together to be a solid. It's becoming more ordered. I'm decreasing the chaos. Okay, greatest entropy again. I got to choose which one out of the following. So I got 1 mole of hydrogen at STP. STP is 25 degrees Celsius. 1 mole of hydrogen at 100 degrees Celsius. It's a lot hotter. Temperature's increasing. This is going to be my winner. Greater temperature and volume. All right. 1 mole of water, solid. 1 mole of water, liquid. Which one is more chaos? My liquid. Greater temperature again, liquid phase. All right. 1 mole of N2O4 at STP or 2 moles of NO2 at STP. Which one has greater chaos? They're both gases. One has more. More molecules, greater volume, more chaos. Predict whether the change in entropy is positive or negative in each of the following processes. So I go from gas to solid. This is going to be a negative because I'm losing the gas phase. I'm going from 2 to 1. All right, so I go from 2 to 3, and I'm going from a solid to gas. It's going to increase. So I'm gaining the gas phase, and I'm increasing by 1 mole. Cooling of nitrogen from 20 to negative 50. So I'm decreasing temperature. I'm going to slow the molecules down, so it's going to be a negative. All right. So let's look at this. Is it a positive entropy or negative entropy? Going from solid, fixed, to all apart. It's going to increase, positive. How about here? I'm going from more open to less open. It's a negative. All right, I'm going from 2 separate things to 1 separate thing. That's a negative. All right, temperature factors. We didn't get this in class. Just know in many systems, temperature will affect spontaneity of a process. For example, like we said earlier, melting ice. Ice spontaneously melts above 0 degrees Celsius. Below 0 degrees Celsius, the opposite process is spontaneous. Meaning, ice melting is endothermic, but increases the chaos of the system. This is an example of a process that has one favorable entropy increase and one unfavorable endothermic condition. So my endothermic is ice melting. You got to add heat to it, which is endothermic instead of releasing heat. That's my endothermic condition that it's needed. But as it melts, it becomes more chaotic. Increase. All right. Gibbs free energy. Don't worry too much about it. Just know that it involves entropy and heat. Gibbs free energy equation mathematically relates the two quantities, delta H and temperature. So if delta G, Gibbs free energy, is negative, the reaction spontaneous proceeds in the forward. If it's positive, it's non-spontaneous, goes in the reverse. So let's see this. If delta H is negative and delta H is negative, endothermic, delta S is positive, so more spontaneity, like Gibbs free, will be spontaneous. So it's delta H, a negative, minus temperature and a positive for this one. So let's look at the next one. I got a negative delta H, gas to a liquid. It's negative. It's not favorable. It's not spontaneous at low temps. This one, unfavorable, because it's positive. Doesn't like it. Favorable delta S, going from this to this, endothermic, spontaneous at high temperatures, and just know this is non-spontaneous. Don't worry about Gibbs free. We're not really going to go over it. Do the worksheet. If you have any questions, please don't hesitate to ask. Hope you guys have a great day.